The floor is yours.
Okay.
Shut down wisdom on us, Gal. I'm so excited about this. Thank you.
Okay, awesome. Of course. And thank you for having me. So yeah, I give this talk at conventions all over the States. I most recently gave it on the Star Trek cruise, the official Star Trek cruise in March of this year. So right under the wire before everything changed. But you know, it was like this nice rush of reality, and then everything changed. So so I'm happy to be here to give this one. Basically, this is my I call it From Tachyons to Warp Drive, Physics in Star Trek. As Dr. Leah mentioned, my PhD is in astrophysics, particularly general relativity. I talk about how you go faster than the speed of light. I talk about how you can you know, time travel, multiverse theory, all those fun things, but we'll go through some of like the realistic and not so realistic aspects of Star Trek. So I am gonna share my slides and we'll kind of jump back and forth between those. If you can give me the ability to screen share, possibly. I think it's under the security options. We're all Zoom experts now. Yeah, okay, so there we go. All right, so can you all still see my face if I'm talking? Just thumbs up. Yeah, okay, great. So this is my Physics in Star Trek talk. We are going to start out talking about transporters. So transporters, these are usually the thing that most people are like, I really want them, because when travel regularly was a thing, I would spend, you know, the equivalent of days each month in airports. And I think a lot of us can sympathize with that. And so people always ask, you know, what's the likelihood that we will get transporters and what's the technology behind them? The interesting thing is that Star Trek kind of contradicts itself when it comes to how they talk about transporters. So we have, you know, an Enterprise vanishing point where Hoshi's like, I'm not getting in that thing because it's going to kill me. It's going to move all my particles and then it's going to rebuild me. And it's a giant death machine. And why would anyone ever step foot in this thing? But, you know, they've used that as well in other places in Star Trek too. And then like in the TNG Second Chances, where we have two Will Rikers show up, they're basically talking about the transporter technology as being something where they break everything down, map where everything is, send that information as data, and then not as data, the android, but as data, computer data, and then rebuild that person out of other material. So like in Second Chances, what happened with Riker was, you know, he was trying to transport off of a planet. They were struggling to get him out, so they made a second beam of data, and then basically one got through, one got reflected back down, and they made 2 copies of Riker. So in that case, they weren't actually transporting the molecules themselves, but more just the information about Riker. So thinking about transporting and maybe possibly what those distance limitations are, when we talk about transporters, they typically consistently say, you know, you have to be at, you have to be in low Earth orbit, essentially. You have to be close to the planet to transport. You can't just transport from, you know, one moon to a planet. You have to be closer to that. But low Earth orbit is, you know, a few hundred miles. It's not insane. So actually going from Starfleet to New Orleans is kind of a good marker for what a transporter distance range was. And the reason I did this was because if you're trying to actually figure out how the transporter technology works, if it's data packets that are being sent, those are going to travel at the speed of light. If it's the particles themselves, they're going to travel slightly slower than the speed of light. So I was trying to figure out the maximum transporter distance to see if there was any there, and there's not. It's basically whether it's the speed of light or a fraction of, going a distance of just under 2,000 miles at or under the speed of light is going to get you about 0.1 seconds to travel, and so, or 0.01 seconds to travel. That's reasonable to disappear and reappear somewhere else. So that doesn't really answer our question, and we're just going to live in the mystery of why, how transporters work, and use them conveniently when we want to. But the big hang up, and the reason that we cannot ever have transporter technology because of physics is due to something called the Heisenberg uncertainty principle. And this is the only equation that I have, I promise. But basically what Heisenberg's uncertainty principle says is that you know where something is. This is your error on its position. This is your error on its velocity or momentum. So the more you know about its position, a particle's position, the less you start to know about how fast it's moving. So it's this trade-off between the two. You can zoom in and say, okay, I know this particle is exactly here, but then you've started to lose information about how fast it's going. It's kind of similar, and I think a lot of people have had those, you know, when they're like deep in their philosophical sort of late teens, early 20s years, going like, but bro, like, dude, have you ever thought about this? Where, you know, you measure something to a foot, but then if you're zooming in, it's like, what really is a foot? And where at the atomic level do you actually measure that? With Heisenberg's uncertainty principle, we're super limited to knowing exactly where a particle is. An analogy for this is a great classic physics joke, so you're welcome ahead of time. Basically says, a police officer pulls over Heisenberg and says, "Sir, do you know how fast you were going?" Says, "Nope, but I know exactly where I am." Continues on to say, "You were going 75 miles an hour. Great, now I'm lost." So that's Heisenberg's uncertainty principle in a nutshell. But how it relates to transporters is that if you're going to map an individual's particles, you want to know where all of those particles exactly are if you're going to break them down and then rebuild them somewhere else. Because of Heisenberg's uncertainty principle, we can't ever know that. But Star Trek, bless Star Trek, because this is like my favorite fix in science fiction for just saying, we know we're breaking physics, but it's science fiction. You're looking at the Heisenberg compensator, an element of the transporter. So they specifically say we have to recalibrate the Heisenberg compensator. They're just acknowledging that they've broken physics, but in the future, they've learned to compensate for it. I'm good with that. I have zero problem with that. So going on from that, I do want to briefly mention that a lot of people, probably about 5 years ago now, saw these headlines about inventing transporter technology. It kind of made the rounds a little bit, saying that, you know, Chinese scientists were able to transport particles from the ground up to a satellite. That was a little clickbaity. What actually happened is that they were able to, and I don't know if this has been replicated, but they were able to sustain quantum entanglement from one place to another. So saying transporter was kind of like this vague approximation for sort of what they were doing. And so just to clarify, we have not at any point invented any kind of transporter technology. All right, now let's go to something a little more ambiguous, photon torpedoes. So photon torpedoes are interesting things to think about. They throw them out all the time, but what actually are photon torpedoes? Because when we see them launched, we see them launched and we see them move and we see them hit things. But photons are light particles. So if it was a packet of light that you were sending, it would travel at the speed of light and it wouldn't look like this sort of physical manifestation. But we can play with this one. This is something where we can kind of let that go a little bit and just stretch our imagination to try to think of how the technology would work. And the way that I've sort of figured it out in my brain, this is not any sort of official explanation, but what you're looking at really is more of a traditional torpedo, traditional weapon that's being launched out. When it looks like this, I sort of think more like plasma. They talk about like proton torpedoes too are mentioned sometimes. That would be more like plasma, superheated ionized gas that's being launched out. It's dangerous, it's very hot, so yeah, that could do damage. But with photon torpedoes, what I think of is it's more like you're sending, in a traditional sort of weapon delivery system, to another ship. When this detonates, then it's kind of like, I mean, you can kind of think of it like a nuclear reaction. You're going to have a high burst of high energy photons that will do a lot of damage. So you have a lot of high energy, this huge release of energy, even if it is like just or mostly photons, is still going to do some damage because you're going from not much to a lot. So that's kind of how I've thought of photon torpedoes. Cloaking devices are something that have been around in Star Trek for a very, very long time, and we love them and we want them. And scientists have tried to figure out how we can make cloaking devices. So this is sort of the first pass at making some sort of cloak in the Romulan sense, that you can wear a jacket, you can put something on, like an invisibility cloak, right? And what it does is it kind of acts like a chameleon would, where it maps the area behind it and then projects that out in front. Doesn't work ideally. So you're not looking at a green screen, you're not looking at any sort of, manipulation here. This is an image of this technology. But I found them. It doesn't work super, super well. You can at least see the outline, but using sort of how chameleons, behave is a way that they've tried to develop cloaking technology. They never really go much into how cloaking technology works specifically in Star Trek. But one of the things that we can think of is that they aren't emitting any sort of electromagnetic radiation. So electromagnetic radiation is light, but that could be heat, that could be visible wavelength, that could be, all these sort of different emission frequencies. That's how we traditionally view stuff in space. When we see things in space, we're either seeing light being emitted from an object, either infrared or visible or any part of the electromagnetic spectrum, or we're seeing light reflected off of an object. So if a ship has a cloaking device, they basically have to mask any emissions that they're giving off, and they also can't reflect anything. They have to be like 100% absorption, and they can't emit anything, which, if you remember black body physics, that's bad because you need to basically put out energy to keep from overheating. But you can extend that, right, to say that, all right, well, they're not in cloak all the time. They have to go into and out of it, and that might be one of the reasons why. But another thing you can think of, if you want to compensate a little bit more for the heat issue, this fact that if you're absorbing all the energy and you're not emitting anything, what if you are still doing that, but you're able to build sort of more of an optical device around your ship that would keep light from actually hitting your ship and going around it? And that's what researchers have done. I think this is Rochester Technology Institute of Technology. But they basically built like an optical setup such that you can look down a lens, a clear lens, down an optical bench, and they've blocked out an entire part of it by just bending and reflecting the light around this area. So you wouldn't be able to see anything that's within this region. There are obviously some flaws with this, such that you have to be looking exactly down this optical bench and you take one step to the left and then you see what's in the middle. But, it's still interesting technology, and it's an interesting application of this. Let me see if I have anything else before I go into, okay, so before I go into more examples, you can give me a thumbs up. Are we okay if we talk Discovery? If people aren't wanting spoilers, give me a thumbs down. Not your opinion on Discovery, but okay, good, thumbs up. So they did the best thing with cloaking devices in Discovery, it actually makes me lose my mind, and I'm so excited about it. So there's this principle, because I don't have any slides for this in the talk because I'm trying, you know, when I give these public talks, some people want to avoid Discovery spoilers still, at least in the last couple of years. But there's a principle called gravitational lensing. I'll show some images in a little bit when we're talking more about space-time, but what they did in Discovery, it basically says that if there's a massive object, light is going to get curved around that massive object. It's going to bend space-time like a bowling ball on a trampoline. Light, as it passes by, is going to get curved and appear to be in a different position. That's how Tilly discovered how to find cloaked Klingon ships. They were basically saying, we need to map the background stars, move, map the background stars, move, map the background stars, see how they're distorted from each angle, and then using the gravitational distortion of the cloaked Klingon ship, we can find them. Brilliant! And again, that sort of lends credence to the idea that, you know, these cloaking devices are specifically for electromagnetic radiation. It doesn't cloak their gravitational presence, and I wouldn't expect it to. So awesome, super fun fact with that. But the examples that we've seen, so first introduced in Balance of Terror, with the Pegasus, this is where they like try to build this tachyon net, and I'm going to talk about tachyons in a little bit, but this is where they were trying to find a way to detect all the cloaked Romulan ships by building this sort of web of tachyons that they would distort it and they would go through. And then there's an episode of Voyager that actually takes cloaking technology like one step further in a really interesting way. And that's a Distant Origin episode. That's where you had these scientists wandering around. There's two Voyager episodes where scientists are wandering around the ship cloaked. They're very easy to mistake. One is the one where they're doing experiments on the crew. That is not this one. This is like the observational, like, not paleontologists, but like archaeologists, sociologists, they're observing the crew, but their cloaking device is slightly offset in time. And I kind of like this because we see things and we interact with things in our universe in a very cause and effect way. When we're kids, you know, part of our mental development is seeing, you know, putting cause and effect together. When I use my muscles to move my hand, I see my hand move in front of my face type thing. But that's all cause and effect because we are seeing the light reflected off of our hand travel at the speed of light when we do that. And so because our brains are kind of used to that, this idea that someone could be slightly out of phase in time, that they're just 1 second, a full second ahead of us, that would be hard to see. We wouldn't see them necessarily. Our brains wouldn't be tuned to that. So it's definitely on the spectrum from science to fiction, and science fiction way on the fiction side, but it's still a really kind of fun way to think about cloaking devices. And I really want to give that an honorable mention, as it were. So getting into the physics of Star Trek, we have planetary scanning all the time, right? We found an M-class planet, which, side note, is purely Star Trek. We do have classifications of stars, and those are G-type, O-type stars. Those are all things. But M-class planets are totally made up for Star Trek, but still fun. But when they scan these planets, that's something that we do all the time, right? And I actually really like this image because these sort of slashed lines that you get across the scan that they've done looks very similar to planetary scanning we do ourselves here on Earth when it comes to particularly weather satellites. Weather satellites orbit in what we call polar orbits. So what they do is they basically go over the poles, the North Pole to the South Pole, and they just stay in one orbit and allow the Earth to rotate under them. So you'll have, if you think of sort of the day-night, you know, line on the Earth, these polar satellites will be oriented in one of those angles. So we talk about like, oh, it's in a morning orbit. That'll be sort of right on the edge, a little bit into the sun of where it's doing its scans, but it just lets the Earth rotate under it, and it visualizes morning throughout the entire Earth as the Earth rotates. But it builds up these scans as it goes. So sort of, you know, it'll be getting 12 hours because it'll map one side and then the other, and then the half will come over to the other side. But it has 12-hour scans, and it builds up imagery of the Earth as it goes. Again, this is a combination of reflected light and emitted light, but it's all passive scanning. It's just imaging, just like they do in Star Trek, and that's totally fine. But the cool thing is, you know, they've talked about planetary scans forever in this, and it's sometimes we have to take that step back and remember that Star Trek came out in 1966. A lot, and things like that were thrown out a long time before that was regular. You know, we did have satellites. We were launching things up into space at that point, but doing regular planetary scans, even of our own planet, was still a little bit of a ways off. So it's always good to remember that. Another piece of technology that we want, but that isn't that far off, is tricorders. So tricorders have been sort of one of these holy grail Star Trek technologies that scientists, people have gone into because they were inspired by Star Trek to try to invent the tricorder. And the idea basically being that you have a handheld device that is completely passive, that's able to get medical information from a patient. If you distill it down to that and say, okay, we're not gonna, you know, shoot for the sun, we're gonna take baby steps here. We're gonna take it one step at a time. Let's invent a passive device that can get some diagnostic information that can be sort of handheld. And they have sort of done that. So there's the Qualcomm literally tricorder X Prize that they did. And I believe, I'm always terrible, I really should just write these numbers down because I'm terrible at remembering them. But it was basically that they had to be able to have a passive device that could get, I think it was something like 8 signatures, 8, you know, like your pulse, the various diagnostic things. I'm very sorry, Teresa. I'm not a medical professional. But that you could basically get these diagnostic information and then also diagnose something like 12 basic diseases off of that. And someone did win that. Now, because the technology is there, doesn't mean that that's available to everyone, because its costs, you know, prohibitive, and it's not that slick, fancy tricorder yet. But that is still something that we work on and that might be achievable possibly in our lifetime, in the same way the flip speakerphone to the Enterprise seemed a long way off, and now we have beyond that. That looks, we're like, hey, remember flip phones, man? So you never know how quickly these things can advance. All right, now we're gonna get to my bread and butter, space-time. Without getting too much into it, space-time is this idea I think a lot of people are familiar with. If you've been to science museums or you've seen sort of talks or TV shows that go into this, this idea of space-time came about in the 19th century from mathematicians, one of whom being Hermann Minkowski, who basically, from a purely math perspective, was starting to think of our universe as 4-dimensional, thinking, all right, if we have 3 dimensions in space and 1 in time, we don't have any control over time, but we can control our spatial dimensions. And trying to think of our universe on this big cosmic scale, just purely from a mathematical perspective. Where Einstein came into it is that Einstein dropped the marble on top of the trampoline, is essentially what his contribution was to that. He said, okay, well, what if we put a bowling ball on this trampoline? What if we introduce mass to this fabric of space-time? And I'll play that again. That you can see that it sort of curves. Oh, I can do this. You can see it bend down. And then Einstein said, okay, well, that's like our planets. That's the sun. That's how the planets go around the sun. This is how the moon goes around the Earth. If you put a bowling ball on a trampoline, you can flick a marble and get it to orbit. The big breakthrough with this was from the fact that Newtonian gravity worked for 99% of stuff. And if we weren't posting this online, I would show the clip from TNG where Data's sitting around the poker table with Newton and Einstein, and they're giving each other a hard time about reference frames, because it's brilliant. But it really comes from this idea of space-time, that Newtonian gravity, thinking of gravity as a force, worked for centuries. Two massive objects are attracted to each other through gravity. It's dependent on their masses and how far apart away from each other that they are. But that didn't work for everything. One of the big things that it didn't work for was Mercury's orbit. As we got better at observing our solar system, we noticed that Mercury's orbit precessed. So it traces out this flower shape as it goes around the sun. And Newtonian gravity does not account for that behavior. But if you've been in a science museum and flicked a marble around a bowling ball, you can get it to precess and go around and trace out this flower shape. So before I continue with this story, I do want to mention the bowling ball and the trampoline does not work for everyone. Some people it's a bad visualization because we've broken down 4 dimensions into effectively like 2.5 dimensions. This might work for you if you're thinking of distorting space-time. So where that bowling ball is the white ball in the middle that's moving, I think of, in a 3-dimensional space, think about mattress springs. You stick your hand in as the mass, grab some springs toward your hand. That's being able to fall in all directions. And that kind of makes it more 3-dimensional and 2-dimensional. If this hurts your head, forget about it. Don't worry about it. Use the bowling ball on the trampoline. No worries there. But the fun thing with this example, so I talked about Mercury's orbit precessing. Astrophysics and astronomy is always this interplay between theory and observation, that because we can't build planets and stars in labs, we kind of have to take these puzzle pieces that the universe gives us, apply the physics laws that we have tested here on Earth to that, see if that passes muster. And if it doesn't, then you look back on those physics laws and kind of see what's different about them. What are the circumstances that are changing in space? And so you're always going back and forth between observation and theory. When it came to Mercury's orbit, that was certainly one of those cases. Telescope technology was better. We were able to observe Mercury pretty well. We could see it precessing, but that didn't fit our physics laws. Just genuinely, Newtonian gravity did not account for that. So without upending all of gravity, they thought, well, what if there's another planet there? Because another planet tugging on Mercury would actually make that pattern occur. And so that held up for a long time before Einstein, and this is my little Easter egg for Star Trek fans, they called it Planet Vulcan. These are star charts from the 19th century where they have Planet Vulcan between Mercury and the sun to account for it precessing as it goes all the way around. But again, Newtonian gravity wasn't allowing that behavior to happen. And as telescopes got better and better, and mathematical understanding, if there was a planet there, we could predict where that planet would be, and we weren't able to see it, and it never showed up. So that's kind of what made everyone think that maybe we have to revisit Newtonian gravity, which is a big deal. That's not insignificant. So when Einstein introduced this idea of space-time and about how mass distorts space-time, one of the first tests they could do is, first they applied it to Mercury's orbit. They said, okay, so if it's just the sun and Mercury, does this make Mercury's orbit work? And it did. That was the first thing Einstein did, was apply it to the masses of the sun and Mercury. And lo and behold, we got this precession behavior. And he celebrated and took 3 days off of work. I would have taken a little longer, but that's just me. But the next so that was sort of a good check in the box, right? But the next big thing that they had to do was sort of test this theory a little bit more. And if the bowling ball did distort space-time the way that we talked about, then we would get that light curvature, this gravitational lensing. So that's what we're seeing here, the stuff I mentioned earlier. This is where the star is over here. As the light passes, it gets bent around, and then we see it here. And because it came from this direction, we think that the star is here, when in reality, it's over here. Now, this effect could only really be seen if we were able to block out the light from the sun to be able to see the stars that are kind of right on that edge. Because we go around the sun, there are different background stars throughout the year that are blocked out by the sun. And so, you know, when we're on one side of the sun, we can look in a direction in space and say, okay, we know all these stars here, we know where they're supposed to be. And then later in the year, when we're back on this side and this area is blocked, we know where those stars should be, but we can't see them because the sun is there. And there was a solar eclipse that happened in 1919, and that's where they thought, great, first test. We'll be able to block out the light from the sun. We'll map all of the stars behind it, see if they appear to be in a different position than they are when the mass of the sun isn't in the way of the light traveling to us. Sent 2 teams out to different parts in the world that were going to see this solar eclipse, frantically map the stars, take pictures. You know, they had like photographic plates at this time. Try to map all of them and see if they were in a different position, and they were. And there was a lot of consternation about that. A lot of people still were kind of, but did you, was that, not super buying it. Since then, scientists have replicated this experiment, and they've actually been able to go back and look at the plates and go, oh yeah, no, they definitely saw gravitational lensing. And so this was sort of another huge check in the box. Since that experiment, 1919, we use gravitational lensing all the time, not just to detect cloaking on ships, but we use it to map out different parts of our universe. So if we have this massive galaxy cluster in the middle, we can see these far distant galaxies behind it, and their light get lensed all the way around. And if they're perfectly aligned, if they're aligned in such a way that they're slightly off axis, you get something called an Einstein's cross, where you see the same image appear like 3 or 4 different places on your screen, but it's the exact same galaxy. And we know that not just because it looks similar, but you know, we can look at the spectral distribution of gases and all the spikes and curves, and you say, okay, no, it's the same one there, the same one there, the same one there. If it's perfectly aligned, you can actually get it to form a perfect circle, and that's pretty darn close to what we got with this image here. So this is an actual image from Hubble. It has a big sort of cluster in the middle here, and then this is a background galaxy that's been curved. The light's just been curved in all directions between it, because it's almost perfectly aligned between us and that point. So this gravitational lensing is really important and interesting, and it's caused by the gravity wells of the masses that are present. So these gravity wells, that's how deep the bowling ball is, right? When the bowling ball is really heavy, it's going to bend the trampoline a lot. If it's less heavy, it's not going to bend it as much. This is a great graphic, and this is, you know, one of those points where I'm glad I can do this virtually, not just to reach more people, but you can actually read some of this stuff. So, but this is from the XKCD comics, and it's showing the relative gravity wells of the different objects in our solar system. So really, really cool stuff. You can see kind of how deep the gravity well is for Jupiter, Saturn, you know, we have Earth over here. And, but the reason I'm pointing this out is because this is the only practical application we actually have right now for Einstein's general relativity. And that's because when you are deeper in a gravity well, you actually experience time slightly slower than you would outside of that gravity well. So when you're here on Earth, our time is actually slightly slower. Seconds are ticking by in a longer time period than they would be if we weren't outside. And that's because of this distortion, this dip in space-time that we have. And over here, you can see these GPS satellites are slightly outside of Earth's gravitational well. We have low Earth orbit way down here. They're effectively on Earth in terms of the gravity well. The ISS is close to Earth. The reason the astronauts on the ISS, the International Space Station, are weightless aren't because they're out away from Earth's gravity well. It's because they're falling around the Earth. They're in free fall around the Earth. They're basically like they've been launched, and when they try to land, the Earth curves away from them. So they're constantly trying to fall, and then the round Earth just keeps falling out from under them. But GPS satellites are not insignificantly further away from our gravitational well, such that time actually goes faster for GPS satellites than it does for us on Earth. And it's fractions of nanoseconds. It's not that much, it's barely noticeable, but it's noticeable if you want your GPS to be precise. And so it's enough to say whether I'm on one side of the street versus the other side of the street, that those time differences need to be accounted for precise GPS. And they do. GPS satellites and our phones actually account for those time differences that they're experiencing because they're inside a gravity well versus not. But we're here to not have a lecture on space-time. We're here to talk Star Trek. So, gravity wells in Star Trek. First one, TNG relics. This is the one where they find in TNG, they find a shuttlecraft that has crashed into a Dyson sphere. They got pulled into the gravity well of a Dyson sphere. They find Scotty. This is the Scotty episode. We remember it not for the Dyson sphere, but for openly weeping for 20 minutes. But Dyson spheres are this, advanced civilization concept that we see throughout science fiction, not just Star Trek, where civilizations have built a sphere around a star to absorb all the energy coming off of it to then power their civilization. And it would be massive, and it would be huge, and it would be easy to fall into that gravity well and not have enough energy to get back out. And that's exactly what happened to Scotty. Oh, blink of an eye. I love this episode. This is the one where Voyager gets stuck, basically gets trapped in the gravitational presence of this planet, and they are experiencing time differently from the people on the surface. I will come back to this one because there are some fine details here that we can break out, and I freaking love it. It's such a good episode. And then we cannot forget Tomorrow's Yesterday and the one with the whales, because they essentially use what we call gravitational slingshotting to go back in time. Gravitational slingshots are a thing. Going back in time with them are not a thing. The best I can do to explain these is just saying, and I'll get to how warp drive works, I think next, but because they're deep in a gravity well, time is beginning to be distorted and then going into a higher warp factor while they're in a gravity well, we can maybe justify it. What I super can't justify is how they get back. So you will let it go. But the whole idea of a gravitational slingshot is seen and is used all the time. This is one of my favorite posters ever. I own this poster. You can find it if you just search for the chart for cosmic exploration. But this is showing the path that every spacecraft we've sent into the solar system has taken. And you can see that these spacecraft have taken these long roundabout paths where they've been gravitationally slingshotted around these planets to adjust their speed and their direction as they're traveling. It's used primarily for speed control, for velocity control, because of the conservation of momentum. Essentially, what they do when they fall into a gravity well and then get launched out, we can picture that, right? You can picture flicking a marble down into a gravity well, having it change direction and shoot off in another way. But the momentum thing is really interesting, that when they get close to this planet such that there's a gravitational exchange happening because of this gravitational well, it's almost like a collision. You can treat it like a collision, and momentum does get transferred, basically, depending on the angle and everything. But the spacecraft can pick up energy from this collision from the planet. It gets transferred. The planet also experiences this collision, but because the mass ratio is so different between this tiny little spacecraft and this massive planet, it's not going to throw the planet off course, even though it has also changed its velocity. Technically, there's been a transfer of momentum. It's so insignificant to the planet, but it does have a significant effect on the spacecraft itself. So that's how we launch stuff out into space. All right, getting around the galaxy. And I don't want to, I know you're all on lunch hours and things like that. So I promise I'll end on time. It's a quirk of mine, but it treats people well. So, so one of the ways we can get around the galaxy without going faster than the speed of light is wormholes. So we are limited to the speed of light purely because we have our surface of space-time. If you have mass, you dip space-time. That's going to slow you down. If you have less mass, you can go faster, but you're still going to be kind of dragging space-time with you a little bit. If you have no mass, you'll coast on the surface of space-time at the speed of light. That's why we can't go faster than that, because mass is a thing, so we're not able to go faster than that. But the ways we can get around it, one of them is wormholes. Wormholes are totally theoretical, but the math checks out, basically, with the theoretical physics. It's saying that, all right, our universe is effectively flat, as much as we've been able to observe. But imagine it's like toilet paper that's been crumpled and laid out on the floor. Overall, it's lying flat, but there might be points that are folded over each other. There might be points that are crinkled, where traveling on the surface would take a long period of time, but you could punch through and actually have a shortcut. And that's effectively what wormholes are. And we see wormholes. Eye of the Needle is one of my favorite Star Trek episodes. This is the one where they find a wormhole that connects the Delta Quadrant to the Alpha Quadrant. It's like their first opportunity to get home in season 1 of Voyager. And they find a Romulan on the other side who's being super Romulan-y. and it turns out that actually it's connected 2 points in space, but it's also connected 2 points in time. And he actually exists 40 years prior to Voyager getting lost in the Delta Quadrant. And that's brilliant. We do see wormholes, the wormhole concept, be treated in science fiction as connecting 2 points in time as well. It's just not something they do as often. It's more convenient to just use it as a tunnel to shortcut areas, but infrequently do we see it treated as connections in time. Unless you have things like, you know, Doctor Who and stuff where that's their entire concept. But another place where we've seen wormholes exist, these are naturally occurring wormholes, is the TNG The Price and the False Prophets. This is a really far apart two-parter episode where the Ferengis went through this wormhole that connected to the Delta Quadrant, and then Voyager ran into them later when they were trapped there. But this is the wormhole that they traveled through, and it was essentially unstable. They had one point was locked, and then the other point appeared in different places, but all just sort of naturally occurring phenomenon. And then there's an entire freaking Star Trek series based on a wormhole. So these are things that we've seen before. And that's, you know, connects the Alpha Quadrant to the Gamma Quadrant. Warp drive, our baby, our favorite thing, warp drive. Warp drive concept basically is saying, all right, we can't travel faster than the speed of light, but nothing says space-time itself can't go faster than the speed of light. So if we build a bubble of space-time around our ship, that can push us faster than the speed of light while we're happily experiencing normal space-time around our own ship. Mathematically, there's some nuances here, but again, nothing we can't break. This is basically showing that you condense space-time in front of the ship, extend it in the back, and it propels you forward faster than the speed of light. If you want to go even faster than that, you can build another bubble around your ship, and that's how you get sort of that warp factor 2, warp factor 3. There are rules that we get. You know, this idea that it's not just instantaneous, that it does take time to travel even at warp. And, you know, it was going to take Voyager 70 some odd years to get home at maximum warp. But yeah, you build these bubbles around your ship. You travel faster. You want to go even faster than that. You build another bubble around your ship. You want to go even faster than that. You build another bubble, and you're exponentially increasing your speed by doing so. And those are our warp factor 2, 3, 4, each bubble that you're building. You do eventually reach the point where you will wrap all of space and time around your ship, because that's how exponents work. And that's warp factor 10, which results in episodes we don't talk about. So, but the concept is sound, the way that they talk about it. All right, so scientists have tried to calculate how we could have warp drive. There is a thing called the Alcubierre Drive, which is sort of that first mathematical calculation for how warp drive would work. When you want to distort space-time, you have to have mass. But we also have mass energy equivalence, this idea that there's energy stored in mass. And if you have an equivalent amount of energy, E equals mc squared, you can distort space-time with that much energy. When they first did the calculations for this Alcubierre drive, they figured out to make those distortions, it would require all of the energy. All the energy, which is not ideal. They since have worked it down to about the energy, at last I saw, they have worked it down to the energy equivalent of the mass of a semi-truck. But the nuclear bombs are the release of the energy stored in a teaspoon of matter. So this is the semi-truck energy equivalent. I'm not strapping myself to that, and I kind of understand Zephyr Cochrane's drinking problem. He's going to strap himself to that. But thankfully, NASA's made of nerds and Star Trek fans who have wanted to pursue this. So they did actually commission an artist to design a ship based on the Alcubierre Drive, and they called it the Enterprise. So we will get there one step at a time. All right, briefly, I just honorable shout out to inertial dampeners, because this is like the Heisenberg compensator. This is saying, all right, inertia is your body's resistance to change in your position or speed. If you want to move, you have to push. Your body naturally doesn't want to. And if you want to stop moving, your body's going to want to keep going. That's why we wear seatbelts. It's all a principle of inertia. If your ship is flying through space at super, even sublight speeds, inertia is a thing that you're going to care about, because you will get pancaked on the back of your starship really fast. But they have inertial dampeners, so we're fine with that. The inertial dampeners absorb that change and make the impact on the bridge and throughout the ship a little bit better. For the sake of time, I won't go into all of my theories on how inertial dampeners can work, but we can do that if we have a chance. All right, I think this is my last, yes, this is my last one. So this is tachyons. Oh, tachyons. Tachyons are actually not a Star Trek construct. They are used in Star Trek all the time, but they are a theoretical particle that has been theorized for decades. They essentially are saying, all right, if we have normal mass to distort space-time down, what if you had negative mass? What if there was a particle that would actually bend space-time the other way, and because of that, constantly travel faster than the speed of light? Remember, our mass bending space-time is what's slowing us down. Tachyons would distort it the other way. They'd like surf on it and always go faster than the speed of light. This breaks a lot of things, but tachyons are used in Star Trek for lots of great examples. But I want to take us back to the blink of an eye. This is what I talked about, where they're trapped in the gravitational presence of this planet, where time is being experienced differently. On the surface of the planet, in blink of an eye, time is going faster than it is for Voyager, the opposite of how we normally see gravitational distortions happening. Remember, time is slower if you're deep, you're stuck in a gravity well. Time goes slower for you. But in this episode, the time actually goes faster than if you're outside the gravity well. And they explain it. The planet has a tachyon core. So its gravitational well does that. Time goes faster for them than it does for the outside. Do not ask me how gravity works on this planet, because the answer is not well, but apparently okay. But I still love that they did account for that difference in the space-time variances by just saying, yeah, it has a tachyon core, so time goes faster for them than it does for the outside. Awesome. All right. The other thing with tachyons is it breaks all understanding of causality. I introduced this as well before, saying that we understand our universe based on the speed of light transferring information, or slower than the speed of light. The speed of light being the limit. If I send a text message, I don't expect my friend to get it before I've sent it. And that's because it takes the speed of light to get there. So this is, again, I have one equation and one graph. This is my one graph. This is something that you have to deal with a lot when you study space-time. And we call these world lines. This is your space dimension. This is your time dimension. And then we have something called the light cone. This is the speed of light. So this is saying that when it comes to causality, I can do something at event A. At some point later, and at some point elsewhere, event B happens. But because event B is within this light cone, it's less than the speed of light to get that information transmitted. A could have caused B. There's no correlation that we've seen, but simply from the fact that enough time has passed until B happened, that there could have been some relation between those. If event C happens sometime after A and at some distance from A, but because it sits outside this light cone, nothing could have traveled fast enough from A to C to have C possibly be caused by A. It happens faster than the speed of light would have transmitted that information. But tachyons live down here. They live outside of the light cone. They're always going faster than the speed of light. So this is where it breaks everything. But Star Trek actually internally uses tachyons really well, which is why so many people think tachyons are from Star Trek. That redemption that's building that web of tachyon beams. Deep Space Nine explorers, this was the fact, like this was using that solar shield to try to, the solar sail, to try to travel the ancient Bajoran ship, got stuck. Tachyons basically punched through it and screwed up their mission. And then in Voyager Endgame, when Admiral Janeway shows up, the first thing they see is a surge of tachyons through this wormhole, indicating time travel's happening. And then when they, when Daniels reveals himself in Enterprise as a time traveler, they know there's a time traveler on the ship because there's an abundance of tachyons there, and nothing would cause tachyons other than time travelers, because time travelers also break all causality. Briefly, the Bajoran Explorers episode, the Bajoran Light Sail, is a thing. This is a thing we have built. The Planetary Society has built a light sail that basically rides in just on radiation from the sun, pushing it through space. And they have successfully launched and operated Light Sail 2 now. There is a, so Star Trek is reality. And with that, thank you. That was fun. All right, I will stop screen sharing. I know I kind of came right up on that wire there, but if Dr. Lee is in charge, so if there are any questions, I'm happy to answer some if we got them.
Oh, yes, exactly. Yeah, everybody can unmute their glorious microphones and ask questions and follow up. First of all, that was fantastic.